What if I told you that the faint glow behind the static on an untuned television holds secrets from the very birth of our universe? That seemingly random noise isn't just interference, it's a message, a whisper from a time when the cosmos was nothing more than a swirling sea of energy before the first stars flickered to life. This is the cosmic microwave background, or CMB, and it's the oldest light we can observe, a staggering 13 billion years old. Think about that for a moment. This signal has traveled across eternity, carrying with it the fingerprints of creation itself, and buried within its subtle fluctuations, a cosmic fossil, a relic so profound it could rewrite our understanding of everything. Picture this: you're holding a photograph, faded and fragile, from a time before history. The edges are worn, the details blurred, but if you look closely, you can just make out the shape of something extraordinary. That's what scientists are doing right now with the CMB. They're not just studying radiation, they're decoding the universe's baby album. Every ripple, every variation in that microwave hum tells a story. Somewhere in that ancient static lies a clue to the very first structures that formed after the Big Bang, the seeds of galaxies, stars, and ultimately, us. It's like finding a hidden chapter in the book of existence, one that's been waiting patiently to be read. So how did this cosmic time capsule survive billions of years? And what can it teach us about where we came from and where we're headed? Buckle up, because we're about to embark on a journey to the edge of time itself. We'll trace the origins of this mysterious signal, uncover how scientists are peeling back its layers, and reveal why this discovery could change everything we thought we knew about the universe. This isn't just a story about astronomy, it's a detective story, a quest to solve the ultimate cold case, the birth of reality, and you're invited to join the investigation. To understand why this ancient light is so special, we have to rewind the clock all the way back to the very beginning. Imagine the universe not as the vast, star-filled expanse we know today, but as an unimaginably dense, searing hot soup of particles. In those first moments, there were no galaxies, no stars, not even atoms, just a churning ocean of energy. Then, around 380,000 years after the Big Bang, something extraordinary happened. The universe cooled just enough for electrons and protons to finally combine, forming the first hydrogen atoms. And in that instant, light, which had been trapped in the chaotic plasma, was suddenly set free. That flash, the moment the universe went from opaque to transparent, is what we're seeing in the CMB. It's the afterglow of creation itself, but here's what's truly mind-blowing. This radiation isn't perfectly uniform. If you look closely, you'll spot tiny fluctuations, warmer patches, and cooler spots like the faint brushstrokes on a cosmic canvas. These imperfections are the fingerprints of the universe's earliest structures, the seeds of everything that came after. The slightly denser regions pulled in more matter over billions of years, eventually giving birth to galaxies and the vast cosmic web we see today. Without those tiny variations, the universe would be a featureless void. No stars, no planets, no us. The discovery of the CMB was almost as serendipitous as the phenomenon itself. Back in 1965, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent hiss in their antenna, a noise they couldn't eliminate, no matter what they tried. At first, they blamed everything from pigeon droppings to faulty wiring, but eventually they realized they'd stumbled onto something far bigger, the echo of the Big Bang itself. Their accidental discovery earned them a Nobel Prize and opened an entirely new chapter in cosmology. Today, satellites like the Planck Observatory map the CMB with breathtaking precision. revealing details finer than the static on an old TV screen. These maps are like ultrasound images of the infant universe, showing us the faint ripples that would one day sculpt the cosmos, and hidden within those ripples, clues to mysteries we're still unraveling: dark energy, dark matter, even the possibility of other universes. The CMB isn't just a relic, it's a Rosetta Stone helping us decode the story of everything. These cosmic fossils are more than just anomalies, they're time capsules from the universe's most violent and creative moments. Imagine pressing your hand into wet cement, leaving behind an imprint that hardens into permanence. The universe did something similar in its first fractions of a second, when quantum fluctuations, tiny, random ripples in the fabric of reality, got stretched to cosmic proportions during a period called inflation. This explosive expansion, happening faster than the speed of light, magnified those microscopic wrinkles into the large-scale structures we now see etched into the CMB. Those faint temperature variations, they're the preserved echoes of quantum chaos frozen into the sky. But one particular fossil stands out like a thumbprint on glass, a mysterious cold spot spanning nearly 2 billion light-years across the southern sky. At first glance, it might seem like just another statistical fluke in the data. Yet when researchers ran the numbers, they found the odds of such a massive anomaly occurring randomly were less than 1 in 50. That's like rolling a die 100 times and never landing on 6 possible but highly improbable. This cosmic cold spot could be evidence of something far stranger, a collision with another universe during inflation, leaving a bruise on our own. Or perhaps it's the shadow of a supervoid so vast it defies our models of cosmic structure. Either way, this fossil challenges our fundamental assumptions about how the universe works. What makes these imprints so revolutionary is how they bridge the unimaginably small with the incomprehensibly large. The quantum fluctuations that seeded them were smaller than a single atom, yet they shaped galaxy clusters hundreds of millions of light-years across. It's as if the universe left us a breadcrumb trail, each irregularity a clue pointing back to physics operating at energies 1 trillion times higher than anything our particle colliders can achieve. Some theories suggest these fossils might even reveal traces of cosmic strings defects in spacetime formed during the universe's phase transitions, like cracks in ice as water freezes. These hypothetical filaments, thinner than an atom but stretching across the cosmos, could have warped the CMB as they vibrated through the early universe. The hunt for these fossils is pushing our technology to its limits. Modern CMB experiments like the Simon's Observatory use detectors chilled to near absolute zero, capable of spotting temperature variations as tiny as 1/1,000,000th of a degree. It's the astronomical equivalent of trying to hear a whisper across a crowded stadium. But with each new generation of instruments, we're peeling back another layer of this cosmic onion, revealing secrets that could upend our understanding of dark energy, quantum gravity, and whether we're alone in the multiverse. Every irregularity in that ancient light is a message in a bottle, one we're just learning how to read. To the naked eye, the cosmic microwave background looks like nothing more than a smooth, unbroken glow, a cosmic fog with no discernible features. But zoom in with instruments sensitive enough to detect variations of just 100,000th of a degree, and suddenly the fog resolves into texture. It's like staring at a seemingly blank sheet of paper, only to realize it's covered in the faintest pencil strokes, each one a blueprint for the universe's grandest structures. These minuscule temperature differences aren't random noise. They're cosmic signposts marking where matter was ever so slightly denser or sparser in the infant universe. Picture the early cosmos as a pot of simmering water, with bubbles forming and dissolving in the heat. Those density fluctuations acted like gravitational anchors, pulling in more matter over billions of years until they became the galaxies and galaxy clusters we see today. The pattern is faint, but it's there, a fingerprint pressed into the fabric of space-time itself. Missions like WMAP and Planck have spent years meticulously charting these fluctuations, creating ultra-precise maps of the CMB's subtle hills and valleys. What they've found is both astonishing and humbling. The overall pattern aligns remarkably well with our models of cosmic inflation, the theory that the universe underwent a mind-boggling expansion in its first fraction of a second. But nestled within that data are stubborn anomalies, wrinkles in the cosmic tapestry that refuse to fit neatly into our equations. Take the so-called axis of evil, an unexpected alignment of large-scale fluctuations that seem to point in a preferred direction, something that shouldn't happen in a universe that's supposed to be uniform in all directions. Or the aforementioned cold spot, a vast region of the sky where the CMB is just a little chillier than it should be. These aren't just statistical quirks, they're potential cracks in the foundation of modern cosmology. If these anomalies aren't mere coincidences, they could be the first hints of physics beyond our current understanding, perhaps even evidence of parallel universes brushing against our own during inflation. The real challenge lies in distinguishing true cosmic fossils from the background noise of the universe. It's like trying to pick out a single whispered conversation in a crowded room. Scientists have to account for everything from the distortion caused by our galaxy's magnetic field to the subtle lensing effect of dark matter bending the CMB light on its 13 billion-year journey to Earth. But with each new observation, we're getting better at isolating the signal from the noise. What makes this search so thrilling is the possibility that one of these anomalies could be the relic we've been searching for, a remnant so profound it forces us to rewrite the textbooks. Maybe it's a trace of primordial black holes forged in the universe's first seconds. Maybe it's evidence of cosmic strings, fractures in space-time left over from the Big Bang. Or maybe it's something we haven't even imagined yet. Every irregularity in that ancient light is a question waiting to be answered, a piece of the puzzle that could reveal how our universe grew from a searing hot singularity into the vast, star-filled expanse we call home. The hunt for cosmic anomalies is like piecing together a jigsaw puzzle where some pieces refuse to fit no matter how hard you try. Astronomers comb through the cosmic microwave background with the precision of detectives examining a crime scene, searching for anything that breaks the expected pattern. And what they've found is anything but ordinary. Take the so-called axis of evil, a bizarre alignment of temperature fluctuations that seem to stretch across the sky in a particular direction. In a universe that's supposed to be uniform in all directions, this is like finding a compass needle pointing to a cosmic north, something that shouldn't exist. Some researchers dismiss it as a statistical fluke, a trick of perspective. But if it's real, it could mean our universe has a preferred orientation, a fundamental asymmetry that would upend our understanding of cosmology. Then there's the infamous cold spot, a chilling mystery lurking in the southern sky. This vast region of space, spanning nearly 2 billion light-years, is noticeably cooler than its surroundings. At first glance, it might seem like just another blip in the data, but the odds of such a massive anomaly occurring by chance are staggeringly low, like flipping a coin 1,000 times and never landing on tails. One wild theory suggests it could be the bruise left by a collision with another universe during inflation, a cosmic fender bender frozen in time. Others propose it's the shadow of a supervoid, a gaping emptiness so vast it defies our models of how matter should be distributed. Either way, this isn't just a curiosity, it's a potential crack in the foundation of modern physics. What makes these anomalies so tantalizing is how they refuse to play by the rules. The standard model of cosmology, built on the idea of a uniform, isotropic universe, struggles to explain them. It's as if the cosmos is whispering secrets we're not yet equipped to hear. Could these oddities be evidence of exotic physics, cosmic strings vibrating through space-time, extra dimensions crumpling at the edges of reality, or even the gravitational echoes of a universe before the Big Bang? Every unexplained fluctuation is a breadcrumb leading us deeper into the unknown. The search for these cosmic irregularities isn't just academic. It's a high-stakes game of hide and seek, where the prize could be a whole new chapter in our understanding of existence. With each new observation, we're not just mapping the ancient sky, we're testing the very limits of our theories, probing for weaknesses that might reveal something extraordinary. And if history is any guide, the universe's greatest surprises often lie in the details we once dismissed as noise. Cosmic inflation was supposed to be the universe's great equalizer, a burst of expansion so violent it would have ironed out all irregularities, leaving the cosmic microwave background smooth as glass. But the universe, it seems, loves throwing curveballs. Those faint wrinkles in the CMB, those stubborn anomalies that refuse to fade into statistical noise, might be more than just imperfections. They could be cosmic hieroglyphics etched into the sky by forces operating before inflation even began. Imagine finding footprints in concrete that was supposed to have dried 1,000,000 years before anyone walked there. That's the scale of this mystery. The cold spot, the axis of evil, the unexpected alignments, these aren't just glitches in the data. They're potential relics from a time before inflation, fragments of a prelude we've never been able to observe. If true, they'd be like finding a fossilized bubble in lava rock, preserving a moment frozen between chaos and order. One radical idea suggests these anomalies could be scars from collisions between our infant universe and others in a multiverse, like bruises from cosmic bumper cars. Or perhaps they're echoes of a phase transition, a moment when the fabric of space-time itself crystallized into a new state, trapping quantum fluctuations like insects in amber. Here's what makes this so electrifying. Inflation was meant to erase all traces of what came before it. The universe's exponential growth should have stretched any pre-existing structures so thin they'd vanish from view. But if these anomalies are real, they slipped through cosmic contraband smuggled across the inflationary border. That means they could hold clues to inflation's ignition switch. Was it a quantum fluctuation that tipped the scales, a collision with another space-time bubble, or something even stranger, like the universe recycling itself from a previous cycle of collapse and rebirth? The implications are staggering. If we're seeing fossils from the universe's first trillionth of a second, we're not just peering further back in time, we're glimpsing energies 1 trillion times beyond what any particle collider could ever recreate. It's like trying to reconstruct a storm from the pattern of raindrops on a window, except the storm was the birth of reality itself. Some theorists even speculate these traces could reveal whether inflation happened in one smooth surge or in fits and starts, with multiple phases of expansion layered like rings in a tree trunk. Yet for all their promise, these cosmic fossils remain maddeningly elusive. Distinguishing them from later distortions like light bent by galaxy clusters or polarized by interstellar dust is like trying to hear a single instrument in a symphony playing backward. New telescopes, like the upcoming CMB S4 project, aim to tackle this with detectors so sensitive they could spot a snowflake's shadow from orbit. What they find might not just solve inflation's puzzles, it could force us to rewrite the universe's origin story entirely. After all, the most profound discoveries often lurk not in the answers, but in the anomalies that refuse to fit. dark matter is the universe's most elusive architect, invisible, untouchable, yet holding entire galaxies together with its gravitational embrace. It makes up over a quarter of everything in existence, yet it leaves no fingerprints on the cosmic microwave background, no heat signature, no light, no direct trace of its presence. But look closer and you'll see its shadow. The gravitational pull of dark matter bends the CMB's light like a lens, warping the ancient photons as they travel across the cosmos. These subtle distortions, called gravitational lensing, are the ghostly imprints of dark matter's hidden hands shaping the universe. Imagine trying to map a city at night by watching how streetlights bend around invisible obstacles. That's what scientists are doing with the CMB. The tiny temperature fluctuations we see aren't just random, they're stretched and twisted by vast, unseen structures of dark matter woven through space. Somewhere in those patterns could lie an even more tantalizing clue: primordial clumps of dark matter, frozen in time from the universe's first moments. These ancient knots, if they exist, would be fossils of a time before galaxies, before stars, when dark matter alone ruled the cosmos. The hunt for these relics is like searching for footsteps in dry sand. Dark matter doesn't collide, radiate, or decay, so its early structures wouldn't leave the same stark imprints as ordinary matter. But their gravity would have subtly tugged at the infant universe, leaving faint ripples in the CMB's fabric. Some theories suggest these ripples could reveal whether dark matter is cold and sluggish or warm and quick-moving, a detail that would rewrite our understanding of how galaxies formed. Others speculate these distortions might hint at dark matter's composition, exotic particles like actions or WIMP, or something even stranger we haven't imagined yet. The stakes couldn't be higher. If we can isolate these cosmic fingerprints, we might finally crack one of physics' greatest mysteries. It's like finding a single smudged letter in a 13-billion-year-old manuscript, one that could tell us why the universe looks the way it does. The CMB isn't just a snapshot of the past, it's a treasure map, and dark matter's signature might be the X marking the spot. Every anomaly, every unexplained warp in that ancient light could be a whisper from the invisible half of reality. And we're just learning how to listen. Among the most tantalizing possibilities hidden in the cosmic microwave background are the ghosts of black holes born in the universe's violent infancy. Not the colossal ones lurking at the centers of galaxies today, but something far stranger: primordial black holes, forged in the searing pressures of the first second after the Big Bang. Picture the universe back then, hotter and denser than the core of a star, with pockets of matter collapsing under their own gravity so intensely they punched holes straight through space-time. These wouldn't be the black holes we know, formed from dying stars. These would be cosmic fossils, relics from a time when the entire universe was denser than a neutron star. What makes these ancient objects so compelling is how they could solve two of astronomy's biggest puzzles at once. If they exist in vast numbers, they might be the invisible dark matter that's been eluding us for decades, each one a tiny gravitational anchor silently shaping the cosmos. Or they could explain the bizarre gravitational wave signals we've detected, collisions between black holes far too small to have formed from stars. The CMB might hold the key, because when these primordial black holes were born, they would have left scars on the fabric of the universe, subtle distortions in the cosmic microwave background that we're only now learning to recognize. Imagine dropping a pebble into a pond and watching the ripples spread. Now imagine that pond is the newborn universe, and the pebble is a black hole condensing out of the chaos. The gravitational pull of that black hole would have warped the surrounding space, leaving a faint imprint on the CMB's light like a fingerprint on glass. Some theories suggest these imprints could appear as circular cold spots in the microwave background regions where the black hole's gravity stretched passing light, redshifting it ever so slightly. Others propose they might create strange, lens-like patterns in the polarization of the CMB, twisting the light's orientation as it passed by. The hunt for these signatures is like searching for bullet holes in a cosmic crime scene. Astronomers are sifting through the CMB's subtle irregularities, looking for patterns that don't fit the usual mold of density fluctuations. Some candidates have already emerged, unexplained cold patches or odd symmetries that could, in theory, be the graves of primordial black holes. But proving it isn't easy. These objects would be incredibly small by cosmic standards, some no heavier than an asteroid yet compressed into a space smaller than an atom. Finding their footprints in the CMB requires separating their signal from the noise of 13 billion years of cosmic evolution. What's truly mind-bending is the scale of time we're dealing with. If these black holes exist, they've been here since before the first atoms formed, silently drifting through the cosmos like shadows. Some might have evaporated by now, thanks to Hawking radiation, leaving behind only a whisper of gamma rays. Others could still be out there, drifting between stars, their gravity subtly tugging at the fabric of reality. The CMB gives us a snapshot of their infancy, a chance to see the universe not just as it was hundreds of thousands of years after the Big Bang, but in its very first chaotic moments. The implications are staggering. If primordial black holes make up even a fraction of dark matter, it would revolutionize our understanding of the cosmos. Instead of exotic particles, the invisible stuff holding galaxies together could be these ancient relics left over from the universe's birth pangs. Or they could be entirely separate, a hidden population of black holes weaving through space, unnoticed until their gravity bends light or ripples spacetime. Either way, the CMB isn't just a relic of the past. It's a detective's notebook filled with clues to mysteries we're only beginning to name. The idea that our universe might not be alone, that it's just one bubble in an endless cosmic foam of parallel realities sounds like science fiction. Yet hidden within the cosmic microwave background could be the proof we've been searching for. Imagine two soap bubbles colliding in midair, their surfaces touching ever so slightly before pulling apart. That fleeting contact leaves a mark, a faint ring of distortion where the membranes briefly merged. Now picture that same phenomenon playing out on a cosmic scale, with our infant universe brushing against another in the chaotic frenzy of inflation. The energy from that collision would ripple through space-time, leaving a scar frozen into the CMB, an imprint we might still detect today. This isn't just wild speculation. The cold spot we've been puzzling over, that vast, inexplicably chilly region in the southern sky, fits eerily well with what such a collision might look like. Simulations show that a clash between universes could create a distinct circular pattern of temperature variations, like a bruise in the fabric of reality. And here's the kicker: the cold spot isn't just cold. It's surrounded by a subtle, ring-like structure, as if something massive once pressed into our universe and left its outline behind. If confirmed, this could be the first tangible evidence that we're part of something far grander, a multiverse where universes bubble up endlessly, occasionally bumping into one another like driftwood on a cosmic tide. But how do we know this isn't just a cosmic coincidence? The math is where things get spine-tingling. The odds of the cold spot appearing randomly are astronomically low, less than 2%. That doesn't prove a multiverse exists, but it makes alternative explanations, like a gargantuan void in space, seem equally bizarre. Either way, we're forced to confront something deeply strange about the cosmos. The real shocker: if this is a collision scar, it means the multiverse isn't just theoretical. It left a dent. The implications are staggering. A confirmed multiverse signature wouldn't just redefine our place in reality, it could unlock secrets about inflation itself. Maybe the energy from that ancient collision triggered our universe's exponential expansion. Or perhaps the cold spot is a window into another universe's physics, revealing laws of nature entirely different from our own. The CMB, in this light, isn't just a relic of our past. It's a message in a bottle from a reality we can't otherwise reach. Of course, skepticism is healthy. Extraordinary claims require extraordinary evidence, and the cold spot could still turn out to be a statistical fluke. But that's the beauty of science at the edge of discovery. Every anomaly is a crossroads, a chance to double down on what we know or venture into the unknown. Right now, telescopes like the Simons Array are scanning the CMB with unprecedented precision, hunting for more of these potential collision scars. If they find even one more, the case for a multiverse goes from speculative to seriously compelling. Think about that for a moment. The same static once dismissed as television noise might hold directions to another universe. It's like finding a letter tucked inside a fossil, a note from a world we never knew existed. Whether this cosmic fossil proves to be a multiverse's calling card or something else entirely, one thing's certain: the universe is still full of surprises. And the biggest one might be written in the coldest patch of sky we've ever found. At the quantum level, empty space is never truly empty. It's a seething ocean of particles flickering in and out of existence, like bubbles forming and popping in a glass of soda. In the universe's first trillionth of a second, these fleeting quantum fluctuations were caught in the ultimate cosmic snapshot. As inflation stretched spacetime faster than light itself, those subatomic ripples didn't just vanish. They were magnified to astronomical proportions, frozen into the fabric of reality like fingerprints pressed into wet clay. Today, we see their echoes in the CMB's temperature variations, each subtle hot or cold spot a quantum hiccup writ large across the sky. What's staggering is the scale of this transformation. A fluctuation smaller than a proton in the early universe could have grown into a galaxy cluster spanning millions of light years. Picture blowing up a microscopic dust mote to the size of a mountain. That's the cosmic inflation equivalent. But here's where it gets even stranger. Most of these fluctuations followed predictable statistical patterns, like the gentle waves on a pond. Yet buried in the CMB's static might lurk outliers, quantum fluctuations so rare they're like rolling a die a billion times and getting nothing but sixes. These cosmic anomalies could be fossils of ultra-high-energy physics, moments when the newborn universe behaved in ways our current theories can't fully explain. One tantalizing possibility is that these rare fluctuations were seeded by exotic particles or forces that only existed during inflation. Imagine a quantum tug of war between dark energy and gravity, creating pockets of spacetime that collapsed or expanded at wildly different rates. Some theories suggest these irregularities might even trace back to quantum entanglement, spooky action at a distance, on a scale encompassing the entire observable universe. If true, the CMB isn't just a relic of the past, it's a quantum experiment frozen in time with the entire cosmos as its laboratory. The hunt for these quantum ghosts is pushing the limits of cosmology. Researchers are scouring CMB maps for statistical anomalies, patterns so unusual they defy inflation's standard predictions. One such fingerprint might be a non-Gaussian signal, a telltale skew in the distribution of hot and cold spots that suggests interactions beyond simple random noise. Finding one would be like discovering a single brushstroke in the Mona Lisa that doesn't match Da Vinci's style, a hint that something deeper lurks beneath the surface. Yet the real magic lies in what these quantum fossils could reveal. If we can decode them, we might glimpse physics at energies a quadrillion times beyond the Large Hadron Collider's reach. They could expose cracks in Einstein's gravity, evidence of extra dimensions, or even the smoking gun for string theory. Every irregularity in the CMB is a message from the universe's first moments, written in a quantum language we're only beginning to decipher. And somewhere in that ancient static, there might be a fluctuation so strange, so improbably rare, that it rewrites our understanding of reality itself. Among the countless particles that flooded the early universe, neutrinos stand out as cosmic phantoms, so light they barely register mass, so elusive they pass through entire planets like ghosts through walls. In the first seconds after the Big Bang, these nearly weightless particles outnumbered atoms by billions to one, streaming through space at nearly the speed of light. Though they barely interact with matter, their collective gravitational pull was enough to nudge the infant universe in subtle ways, leaving faint brushstrokes on the cosmic microwave background. Today, those imprints might be our best window into the behavior of neutrinos at energies no lab on Earth could ever replicate. Think of the early universe as a crowded dance floor, with particles jostling in a frenzy of heat and motion. Neutrinos were the wallflowers rarely colliding with others, yet their sheer numbers meant they swayed the rhythm of the entire room. As the cosmos expanded and cooled, these particles began traveling freely, their gravity subtly tugging at the denser regions of matter. This gentle pulling altered how structures formed, leaving a distinctive signature in the CMB's temperature fluctuations. It's like detecting the whisper-thin shadow of a dancer who left the ballroom 13 billion years ago. The real magic lies in what these neutrino fossils could reveal. Modern detectors on Earth can study neutrinos from the sun or nuclear reactors, but those particles are mere shadows of their primordial selves. The neutrinos imprinted on the CMB carry traces of their ancient energy, a time when they were 1 trillion times more powerful than anything we can produce today. If we can decode their faint fingerprints, we might unlock secrets about neutrino mass, a puzzle that still baffles physicists. Why do these particles have any weight at all? How do they oscillate between different types? The CMB could hold clues written when these particles were at their most energetic. One tantalizing possibility is that cosmic neutrinos interacted with forces we've never detected, perhaps relics from a time before the standard model of particle physics took shape. Some theories suggest they might have bumped into hypothetical particles like actions, or even left traces of a long-lost symmetry between matter and antimatter. The CMB's subtle distortions could be the only remaining evidence of these interactions, like finding a single faded receipt from a transaction that happened at the dawn of time. The hunt for these neutrino whispers is pushing our observational tools to their limits. Telescopes like the upcoming CMB-S4 will scan the sky with unprecedented precision, searching for telltale smudges in the microwave background's polarization, a potential smoking gun for neutrino interactions. Other experiments are combing through the CMB's statistical patterns, looking for anomalies that might betray where neutrinos slowed the growth of galaxy clusters. It's forensic astronomy on the grandest scale, reconstructing events that unfolded in the universe's first second using only the faintest of echoes. What makes this search so thrilling is its potential to bridge two seemingly disconnected worlds, the quantum realm of tiny particles and the vast expanse of cosmology. Neutrinos are the ultimate messengers, carrying news from an era when the entire universe was smaller than a grapefruit. If their cosmic fossils can be read clearly, they might not just solve mysteries about particle physics, they could rewrite the story of how everything we see came to be. The universe has left us a trail of breadcrumbs, and neutrinos might be the guide we've been waiting for. The cosmic microwave background isn't just a sea of ancient light, it's a tapestry woven with hidden polarizations, subtle twists in the light's orientation that could hold the key to the universe's most explosive secret. When we talk about polarization, think of sunlight reflecting off a lake. The glare isn't just bright, it's organized, vibrating in a particular direction. The CMB has its own version of this, but with a cosmic twist. Some of its light waves don't just vibrate randomly, they align in patterns called E modes and B modes. And buried within those B modes might be the faintest ripples of all, gravitational waves from the universe's first trillionth of a second. Here's why that's revolutionary. Inflation, the theory that the universe expanded faster than light in its infancy, predicts that quantum fluctuations would have stretched into gravitational waves, ripples in space-time itself. These waves would have left a distinct swirl-like pattern in the CMB's B-mode polarization, like fingerprints on a cosmic magnifying glass. Spotting that pattern wouldn't just confirm inflation, it would give us a snapshot of the universe when it was smaller than a proton, a moment so fleeting we've never had a window into it before. But the universe loves a challenge. These primordial B modes are buried under layers of cosmic noise, galactic dust, magnetic fields, even the gravitational lensing of later epochs. All of them create their own B-mode signals, like static drowning out a whisper. Separating the true inflationary signal from this chaos is like trying to hear a single violin in a symphony played at the bottom of the ocean. The most famous attempt, the BICEP 2 experiment in 2014, initially claimed a detection only to realize they'd been fooled by interstellar dust. Yet the hunt isn't hopeless. New generations of telescopes, like the Simons Observatory and LightBird, are deploying with sensitivities orders of magnitude better than their predecessors. They're not just looking for B modes, they're hunting for a specific curl in the polarization, a signature so unique it can't be mimicked by dust or galaxies. If they find it, the implications would be staggering. We'd have direct evidence of inflation's energy scale, a measure of how violently spacetime stretched in that first instant. It could even hint at quantum gravity, the holy grail of physics, by showing how gravity behaved when it was tangled with quantum effects. What makes this search so thrilling is the sheer audacity of what we're trying to see. These gravitational waves would have originated at energies 100 trillion times higher than anything our particle colliders can reach. They're fossils of a time when the universe was so hot and dense that the fundamental forces gravity, electromagnetism, the strong and weak nuclear forces might have been unified into a single, sublime symmetry. The B modes are more than just a signal. They're a message from the edge of physics itself, written in the language of spacetime's vibrations. And if we never find them, that would be just as profound. A null result would force us to rethink inflation, perhaps even consider wild alternatives like a bouncing universe or a cyclic model. Whether the B modes appear or stay hidden, they're forcing us to confront the deepest questions about reality. After all, the most tantalizing fossils aren't always the ones we find sometimes. It's the ones we can't that rewrite history. We're used to thinking of the Big Bang as the ultimate starting line, the moment everything began. But there's a shadowy realm even before that, a sliver of time so unimaginably brief it makes a nanosecond feel like an eternity. This is the Planck epoch, the universe's first 10 to the power of negative 43 seconds. To put that into perspective, if you condense the entire history of the cosmos into a single year, the Planck epoch would last less than a trillionth of a blink. Yet within that fleeting instant, the seeds of everything, every galaxy, every star, every atom might have been sown. What makes this era so enigmatic is that our physics simply breaks down here. Gravity, usually the weakest of forces, would have been as powerful as the other fundamental forces, tangled together in a unified superforce we can't yet describe. Space and time as we know them wouldn't exist yet. Instead, the fabric of reality would have been a seething quantum foam, with space-time itself bubbling and fluctuating like a pot of boiling water. It's a realm where the very concepts of before and after lose meaning, where the universe was so small and dense that quantum effects governed everything. And somehow, buried in the cosmic microwave background, there might be a whisper from this primordial chaos, a fossil from the edge of time itself. The idea isn't as far-fetched as it sounds. Just as a tree's rings record droughts and storms from centuries past, the CMB could bear scars from the universe's violent infancy. Some theorists speculate that certain anomalies, like the cold spot or unexpected alignments in the microwave background, might be imprints of quantum fluctuations that arose during the Planck epoch. These wouldn't be ordinary fluctuations, though. They'd be relics of a reality where gravity operated on the same scale as quantum mechanics, a regime no experiment on Earth can replicate. Finding one would be like uncovering a letter written in a lost language, one that holds the key to a theory of everything. Imagine if one of these cosmic fossils turned out to be evidence of a primordial black hole, a tiny knot of space-time that formed when the universe was smaller than an atom. Or perhaps it's a signature of cosmic strings, filaments of pure energy thinner than a proton but stretching across the cosmos, vibrating like guitar strings and warping the CMB as they go. These aren't just wild guesses, they're testable predictions. If such structures exist, they'd leave distinct patterns in the microwave background, subtle enough to have gone unnoticed until now but unmistakable once we know what to look for. The real challenge is separating these Planck-era relics from the noise of later cosmic events. It's like trying to pick out the sound of a single raindrop from a recording of a thunderstorm. But next-generation telescopes like CMB-S4 and the proposed PICO satellite are being designed to do just that. With sensitivities fine enough to detect temperature variations of a few billionths of a degree, they could spot the faintest echoes of quantum gravity, clues to how space-time itself was woven into existence. What's at stake isn't just a deeper understanding of the Big Bang. If we can find evidence from the Planck epoch, it could bridge the greatest divide in modern physics, the chasm between Einstein's theory of gravity and the quantum mechanics of the very small. Right now, these two frameworks are like different languages, each describing a piece of reality but refusing to translate neatly into the other. A cosmic fossil from the universe's first second might finally give us a Rosetta Stone, a way to read both at once. Think about that for a moment. The same static once dismissed as meaningless noise could contain a message from a time before time, a relic of forces so alien we've yet to name them. Whether it's a twist in the CMB's polarization, an odd clustering of hotspots, or some anomaly we haven't even imagined yet, the hunt for this fossil isn't just about peering into the past. It's about uncovering the rules of a game we didn't know we were playing, the hidden physics that birthed reality itself. And somewhere in that ancient light, the answer might be waiting. Hidden within the cosmic microwave background might be the scars of a cosmic catastrophe, not a collision or explosion, but something far stranger, cracks in the very fabric of space-time. These hypothetical fractures, known as cosmic strings, are thought to be relics from the universe's earliest moments, when reality underwent a dramatic phase transition. Picture the universe cooling like molten metal, its fundamental forces crystallizing into the patterns we know today. Just as ice forms cracks as it freezes, space-time itself might have developed defects, one-dimensional filaments of pure energy, thinner than a proton but stretching across the entire cosmos. If they exist, these strings would be unimaginably dense, packing the mass of a mountain into a length smaller than an atom. And their gravitational pull could have warped the CMB, leaving behind telltale linear distortions like the wake of a ship frozen in an ancient sea. The idea isn't as outlandish as it sounds. We see phase transitions everywhere in nature, water turning to ice, magnets aligning as they cool. The early universe likely underwent similar shifts as it expanded and cooled, with the fundamental forces separating from their primordial unity. Cosmic strings would be the cosmic equivalent of cracks in a cooling slab of concrete, flaws that formed as the universe settled into its current state. What makes them so tantalizing is how they'd interact with light. A cosmic string's immense gravity would bend space-time around it, creating a lens-like effect. As CMB photons passed near one, their paths would twist slightly, leaving faint, razor-straight lines of temperature variation in the microwave background, anomalies that can't be explained by ordinary density fluctuations. Hunting for these strings is like searching for invisible wires in a dark room by watching how dust motes swirl around them. Scientists have developed sophisticated algorithms to scan CMB maps for suspiciously linear features, ruling out more mundane explanations like galaxy clusters or instrumental noise. One candidate, a peculiar cold streak in the CMB, even matches predictions for what a string's signature might look like, a cosmic scratch across the sky. But proving it's real requires ruling out every other possibility, a painstaking process that's still underway. The implications of finding a cosmic string would be staggering. These aren't just oddities, they'd be direct evidence of physics at energies we can't possibly recreate on Earth. Their existence would confirm that the universe underwent dramatic phase transitions in its infancy, locking away energy in cosmic-scale defects. Some theories even suggest these strings could be the seeds of supermassive black holes or the hidden drivers of dark matter. And because they're predicted by many unified field theories, discovering one could point us toward the long-sought theory of everything, a framework tying together quantum mechanics and gravity. Yet cosmic strings are slippery prey. Unlike black holes or galaxies, they'd emit no light, no radiation, just subtle gravitational nudges. Their fingerprints in the CMB would be whispers in a hurricane of data. But with next-generation telescopes like the Simons Observatory sharpening our view of the microwave background, we might finally spot their ghostly trails. Imagine tracing one of these filaments back to its origin, following a crack in reality to the universe's first trillionth of a second. It's a reminder that sometimes the most profound truths aren't written in stars or galaxies, but in the faintest imperfections, the cosmic equivalent of a seam in the tapestry of spacetime. The cosmic microwave background's near-perfect uniformity isn't just a curiosity, it's a riddle that cuts to the heart of existence. Why does the universe appear so meticulously balanced, with conditions so precisely tuned that even a slight deviation would have made stars, planets, and life itself impossible? This is the problem of fine-tuning, and the CMB is our Rosetta Stone for decoding it. Those tiny temperature fluctuations we've been exploring, they're not just ancient relics, they're the cosmic equivalent of a precision instrument, calibrated to 1 part in 100,000. For comparison, that's like throwing a dart across the Milky Way and hitting a bullseye the width of a hydrogen atom. But here's where it gets unsettling. Such perfection seems astronomically unlikely unless something tipped the scales. One possibility is that we're seeing the fingerprints of deeper physics, perhaps even evidence of a multiverse. Imagine a cosmic lottery with infinite tickets, each representing a universe with randomly dialed physical constants. Most would be barren voids or collapsing messes, but a rare few like ours would hit the jackpot for life by sheer chance. The CMB's uniformity could be the winning ticket, a statistical fluke in an endless sea of failed universes. Alternatively, the answer might lie in the elegant symmetries of string theory, where the universe's fine-tuning isn't accidental but inevitable, woven into the very fabric of higher dimensional geometry. Some versions of the theory predict that the universe selects stable configurations naturally, like a marble settling into the bottom of a bowl. If true, the CMB's smoothness might reflect this cosmic equilibrium, a default setting baked into reality's code. Yet there's a third, more provocative interpretation. What if the fine-tuning isn't random or inevitable, but intentional? Not necessarily in a mystical sense, but as a consequence of undiscovered physics that actively shaped the early cosmos. Some theories propose self-correcting mechanisms like a universe that rewrites its own initial conditions to achieve stability. Others suggest observational bias. We can only measure this universe because we're here to see it, an idea known as the anthropic principle. The key to unraveling this mystery might lie in those stubborn CMB anomalies, the cold spots, the unexpected alignments, the statistical outliers. If they're truly fossils from the universe's first moments, they could reveal whether fine-tuning was a roll of the dice, a law of nature, or something even stranger. Future telescopes like the CMB S4 project aim to scrutinize these anomalies with unprecedented precision, searching for patterns that defy conventional explanations. A single irregularity in the wrong place or the right one could force us to rethink whether our universe is a solo act or one verse in a grand cosmic chorus. What's at stake isn't just academic. If the multiverse exists, our place in reality becomes both humbling and exhilarating, a rare oasis in an infinite desert. If string theory's symmetries hold, we might finally glimpse the unity underlying all forces, and if the tuning points to something deeper, well, that could be the most profound discovery of all, a clue that the universe knows how to build a home. Einstein's theory of general relativity has been astronomy's gold standard for over a century, shaping everything from GPS satellites to our understanding of black holes. It paints gravity not as a force, but as the bending of spacetime itself, a cosmic trampoline where planets and stars create dips that guide the motion of everything around them. And when it comes to the cosmic microwave background, relativity works remarkably well, predicting the broad strokes of those temperature fluctuations with stunning accuracy. But what if the universe left us a clue that gravity isn't quite what we thought? Hidden in the CMB's faint anomalies might be deviations so subtle they've gone unnoticed, hints that on the largest scales, gravity plays by different rules. Take dark energy, for example. This mysterious force accelerating the universe's expansion fits neatly into Einstein's equations as a cosmological constant. But what if it's not some exotic energy at all? Alternative theories like modified Newtonian dynamics or MUND suggest that gravity itself might behave differently at cosmic distances, eliminating the need for dark energy entirely. The CMB could hold the key because if gravity were subtly stronger or weaker across vast reaches of space, it would leave fingerprints in how those ancient photons traveled to us. Imagine throwing a ball and expecting it to follow a predictable arc, only to watch it swerve inexplicably at the last second. That's the kind of anomaly cosmologists are hunting for in the microwave background. One tantalizing possibility involves the way galaxies cluster on enormous scales. General relativity predicts how matter should clump together over time, shaping the CMB's patterns in a specific way. But some measurements show slight discrepancies, galaxies grouping a bit more or less than expected, like a choir singing just off-key. These mismatches could be statistical noise, or they might signal that gravity weakens or strengthens over distances larger than our solar system. The CMB's lensing patterns, where gravity bends its light, are particularly telling. If those distortions don't align with relativity's predictions, it could mean spacetime bends differently than Einstein imagined when stretched across billions of light years. Then there's the elephant in the room, dark matter. This invisible substance outnumbers ordinary matter 5 to 1, yet we've never directly detected it. Modified gravity theories argue that what we call dark matter might just be gravity acting in ways we don't yet understand. If that's true, the CMB's subtle ripples should reflect a universe where gravity's rules shift at certain scales, like finding footprints that suggest the walker changed stride mid-step. Some researchers are already sifting through Planck satellite data for these cosmic breadcrumbs, searching for patterns that defy conventional models. The stakes couldn't be higher. If the CMB's anomalies do point to revised gravity, it wouldn't just tweak Einstein's theory, it would rewrite the cosmic playbook. Suddenly, phenomena like galaxy rotation curves or the universe's expansion might not require invisible substances or mysterious energies. Instead, we'd be confronting a fundamental change in how space-time itself behaves. It's the difference between inventing an invisible ink to explain missing words in a letter and realizing the pen writes differently under certain conditions. Yet skepticism is healthy. General relativity has passed every test thrown at it for generations, from bending starlight during eclipses to predicting gravitational waves. Dethroning it would require ironclad evidence, the kind that survives relentless scrutiny. That's why next-generation CMB experiments are doubling down on precision, mapping the microwave sky with resolutions sharp enough to spot the faintest gravitational quirks. Whether they confirm Einstein's triumph or uncover his theory's limits, one thing's certain: the universe's oldest light still has secrets to spill, and some of them might be written in the language of gravity itself. Dark energy is the universe's most elusive architect, pushing galaxies apart faster and faster, yet revealing almost nothing about itself. It makes up nearly 70% of the cosmos, yet unlike dark matter, it doesn't clump or distort. It's a ghostly presence felt only by its relentless push against gravity's pull. But here's the twist: the cosmic microwave background might be hiding its earliest fingerprints. Those faint temperature fluctuations we've been decoding, they could carry whispers of dark energy's infancy, back when the universe was a fraction of its current size, and this mysterious force was just beginning to stir. Think of dark energy as a silent conductor, orchestrating the universe's expansion without leaving sheet music behind. For billions of years, gravity dominated, pulling matter together into galaxies and clusters. Then, around 5 billion years ago, something flipped. Dark energy took over, and the cosmos began accelerating outward. But what if its influence started much earlier, subtly tweaking the universe's growth even in those first moments? The CMB's patterns could hold the answer. When light from the Big Bang's afterglow finally broke free, dark energy, though weak at the time, might have already left a faint mark on how structures formed. It's like finding a child's scribble in the margin of an ancient manuscript, a hint of something grander to come. The key lies in the way dark energy affects spacetime itself. If it's truly a constant force, as Einstein's cosmological constant suggests, its early presence would have ever so slightly altered how matter clumped together in the universe's first chapters. Those changes would ripple into the CMB's fluctuations, creating tiny deviations from what standard models predict. Imagine baking a cake where one ingredient, barely noticeable at first, changes how the entire dessert rises. Dark energy could be that ingredient, and the CMB is our cosmic oven mitt, still warm from the universe's earliest bake. But what if dark energy isn't constant at all? Some theories propose it's a dynamic field, evolving over time like a river changing its course. If that's true, its signature in the CMB would be even more dramatic. Certain anomalies like unexpected large-scale patterns or odd alignments in the microwave background could be echoes of dark energy's awakening, moments when its strength shifted in the cosmic dawn. It's as if we're listening to a recording of the universe's first heartbeat, searching for the skipped beat that hints at a hidden condition. The hunt for these clues is like trying to spot a single altered pixel in a century-old photograph. Scientists comb through CMB data, comparing the observed patterns against countless simulations, some with dark energy acting early, some without. The differences are minuscule, but modern telescopes are reaching the precision needed to spot them. Projects like the Simons Observatory and Future CMB-S4 aim to measure the CMB's polarization and temperature fluctuations with such accuracy that even dark energy's quietest whispers might finally be heard. What's at stake isn't just understanding why the universe accelerates. If dark energy's fingerprints are truly there, etched into the CMB, we might finally learn whether it's a static feature of space-time or something far stranger, a field that decays, interacts, or even connects to other dimensions. The cosmic microwave background isn't just a relic of the past. It's a time capsule waiting to crack open, holding secrets about the universe's fate. And somewhere in that ancient light, dark energy's first breath may still linger. Detecting a cosmic fossil in the CMB is like trying to hear a whisper in a hurricane. The signal we're after isn't just faint, it's buried under layers of cosmic interference, from the glow of distant galaxies to the static of our own Milky Way's magnetic field. Even the most subtle anomalies, those potential relics from the universe's first moments, are swamped by noise 1,000,000 times louder than the whispers we're straining to hear. It's the ultimate needle in a haystack challenge, except the haystack is the entire sky, and the needle might not even be there. This is where modern astronomy pushes the limits of engineering and imagination. Current telescopes like Planck and ACT have mapped the CMB with astonishing precision, spotting temperature variations as tiny as 1 part in 100,000. But to uncover the deepest cosmic fossils, those primordial imprints that could rewrite physics, we need to do better, much better. Enter CMB-S4, the next generation of observatories designed to scan the microwave sky with resolution so sharp it could spot a snowflake on the moon. These instruments will deploy arrays of superconducting detectors, chilled to near absolute zero, capable of measuring temperature fluctuations down to a few billionths of a degree. They'll filter out galactic dust with unprecedented accuracy, untangle the web of gravitational lensing, and isolate the faintest whispers of inflation-era physics. Yet, even with this staggering sensitivity, success isn't guaranteed. The universe has a habit of hiding its most precious secrets just beyond our reach. Take primordial gravitational waves, for example, the elusive B-mode polarization patterns that could prove inflation happened. Despite decades of searching, they've remained stubbornly invisible, masked by confounding signals from interstellar dust. It's a reminder that nature doesn't care about our deadlines or wishful thinking. The fossil we're hunting might be there, etched into the CMB's ancient light, or it might be a ghost, a theoretical phantom that slips through our nets no matter how finely we weave them. What makes this pursuit so electrifying isn't just the potential discovery, it's the sheer audacity of the attempt. We're building machines to interrogate the first trillionth of a second of existence, to read quantum fluctuations stretched across the cosmos like cosmic graffiti. If we succeed, the payoff could be monumental, evidence of parallel universes, cracks in space-time, or forces that vanished before the first stars ignited. But even failure would be illuminating. If CMB-S4 scans the sky and finds nothing where anomalies should be, it might mean our theories are fundamentally flawed, that the universe's origin story needs a radical rewrite. So the question isn't just whether we'll find the fossil, it's whether we're asking the right questions in the first place. The CMB is more than a relic, it's a mirror, reflecting back not just the universe's beginnings but the limits of our own understanding. And sometimes the most profound revelations come not from the answers we uncover, but from the mysteries that refuse to be solved. Separating a true cosmic fossil from the background noise of the universe is like trying to identify a single voice in a stadium full of cheering fans. Every flicker in the cosmic microwave background could be a relic from the dawn of time, or it could just be the static hum of our own galaxy, the afterglow of distant quasars, or even the faint tremble of Earth's atmosphere interfering with our telescopes. The challenge isn't just technical, it's philosophical. How do we know when we've found something real and not just a trick of the data? The answer lies in a marriage of cutting-edge statistics and old-fashioned skepticism. Astronomers don't just scan the CMB for oddities. They bombard the data with thousands of simulations, testing whether any anomalies could arise by pure chance. It's like shuffling a deck of cards over and over to see if the same improbable hand appears twice. Some teams use machine learning, training algorithms to recognize the subtle fingerprints of primordial physics hidden in the noise. Others employ blind analysis techniques, where researchers deliberately hide key details from themselves to avoid subconsciously cherry-picking results. The goal isn't just to find something strange, it's to prove that strangeness couldn't have happened randomly. Take the infamous cold spot, for example. At first glance, it looks like a compelling fossil, a vast, unexplained chill in the CMB. But could it just be a statistical fluke? To find out, scientists generated millions of mock universes in supercomputers, each with random fluctuations mimicking the CMB's expected behavior. Less than 2% of these simulations produced anything as extreme as the cold spot, making it unlikely, but not impossible to occur naturally. That's the razor's edge cosmologists walk, distinguishing the one in a million signal from the million other signals that look just like it. The interference doesn't stop at cosmic sources. Even the most advanced telescopes introduce their own noise. Detectors might misfire, electronics could drift, or stray heat might creep into the system. To combat this, experiments like the Simons Observatory use layers of redundancy, cross-checking measurements across multiple instruments to cancel out errors. It's like trying to hear a whisper in a windy field by planting dozens of microphones, each one confirming whether the sound is real or just the rustling of grass. What makes this hunt so exhilarating is the stakes. A single verified anomaly could rewrite our understanding of the universe's birth, but the flip side is equally profound. If every oddity eventually fades into statistical noise, that too would tell us something startling. Perhaps the universe is simpler or far stranger than we've dared to imagine. The CMB isn't just a static-filled relic, it's a mirror, reflecting back both the cosmos's secrets and the limits of our own perception. And in that reflection, we might just discover something unexpected about ourselves. Theoretical models of the early universe paint a wild menagerie of possible cosmic fossils, each one a ghostly imprint from an era when reality operated under different rules. Some predict topological defects, like cosmic textures, wrinkles in spacetime left over from phase transitions in the primordial fireball. These wouldn't just dimple the cosmic microwave background, they'd create sharp, circular temperature variations, like ripples from a stone dropped into the universe's first liquid moments. Others suggest magnetic monopoles, hypothetical particles with a single magnetic pole that could have clustered in the early cosmos, their gravity subtly warping the CMB's light like invisible lenses. Then there are domain walls, vast membranes separating regions of spacetime that crystallized with different properties, potentially leaving sheet-like scars across the sky. What makes these theoretical relics so thrilling is how precisely their signatures are calculated. A cosmic texture, for instance, would produce a distinct bullseye pattern in the CMB, a hot ring surrounding a cold core, the aftermath of spacetime snapping like an overstretched rubber band. Magnetic monopoles, if they exist, would distort the background radiation in a way that depends on their mass and abundance, like finding footprints that reveal not just the presence of a creature, but its weight and stride. Domain walls would show up as razor-thin temperature discontinuities, as if someone took a knife to the fabric of the early universe and left the edges slightly frayed. The stakes couldn't be higher. If we found a texture's bullseye, it would confirm that the universe underwent a specific kind of symmetry breaking in its infancy, a cosmic phase transition akin to water freezing into ice. A monopole's fingerprint would validate grand unified theories, bridging the electromagnetic and nuclear forces, and a domain wall that could hint at extra dimensions, hidden layers of reality folded into the fabric of spacetime. Each fossil is a cipher, a piece of evidence locked in a 13-billion-year-old case file. But here's the catch: many of these relics would have been diluted or erased by inflation, the universe's explosive early growth spurt. If inflation lasted too long, it would have stretched any primordial defects into oblivion, like smoothing out wrinkles in a tablecloth by yanking it taut. That's why finding one would be a bombshell. It would mean inflation wasn't as all-encompassing as we thought, leaving behind pockets where the old physics still lingered. The hunt is already underway. Teams scour CMB maps for telltale patterns, running algorithms designed to spot the subtle fingerprints of these ancient relics. Some have even claimed tentative detections, a handful of circular anomalies in Planck satellite data that resemble textures, or odd polarization patterns that could hint at monopoles. But extraordinary claims require extraordinary evidence, and so far, nothing definitive has emerged. The next generation of telescopes, like CMB S4, will bring even sharper vision to this search, peeling back layers of cosmic static to reveal whether these theoretical ghosts are real. What's fascinating is how these fossils don't just test one theory, they pit entire frameworks against each other. If we find a texture, it supports certain grand unified models while ruling out others. A monopole detection could mean the universe cooled in a specific sequence, locking in clues about forces we've never directly observed. And if we find nothing, that silence would speak volumes, forcing us to reconsider whether our cosmic timeline is missing a chapter. In the end, it's not just about validating a single idea. It's about piecing together the universe's lost history, one anomaly at a time. Whether the fossil we uncover is a texture, a monopole, or something entirely unexpected, the discovery won't just fill a gap in our knowledge, it could tear open a new frontier. After all, the most profound revolutions in science often begin with a single, stubborn anomaly that refuses to go away. The cosmic microwave background has already rewritten the textbooks, transforming cosmology from speculation into precision science. It confirmed the Big Bang not as a theory but as observable history, pinned down the universe's ingredients to within decimal places, and even revealed the invisible scaffolding of dark matter. Yet for all its revelations, the CMB feels less like a finished story and more like an opening chapter, one where the next sentence could shatter everything we think we know. A genuine cosmic fossil wouldn't just add to our knowledge, it would crack open entirely new realms of physics, from hidden dimensions to particles that defy the standard model. Consider how much we've gleaned from subtle asymmetries already. Those tiny temperature fluctuations in the CMB didn't just confirm the universe's composition, they exposed its geometry. The way light from the early cosmos bends and dims tells us space isn't curved like a ball but flat as a sheet, at least within the limits of our measurements. Yet flatness raises its own paradox. For the universe to be this finely balanced, something must have fine-tuned it to 1 part in 10 to the power of 60. That's like balancing a pencil on its tip for billions of years. Inflation offers one explanation, but what if the CMB's deeper anomalies hint at another? A cosmic fossil might reveal whether this precision is a fluke, a necessity, or the signature of something beyond our 3 dimensions. Then there's the puzzle of quantum gravity. The CMB's patterns were set when the universe was smaller than an atom, a realm where gravity and quantum mechanics should have clashed violently. Yet somehow, those quantum wrinkles stretched smoothly across the cosmos without tearing spacetime apart. It's as if the universe knew how to translate between these 2 incompatible languages long before physicists realized they were speaking them. A primordial relic in the CMB could be the missing dictionary, a clue to how gravity behaves at scales where space and time lose meaning. Perhaps the cold spot isn't just an oddity but a scar from where quantum foam crystallized into the spacetime we recognize. The most tantalizing possibilities lie beyond our current frameworks. What if the CMB's polarization patterns hide traces of pre-Big Bang physics, echoes from a time before time? Some models suggest our universe is a bubble in an eternal multiverse, with collisions leaving faint bruises in the microwave background. Others propose that dark matter isn't a particle at all but a shadow cast by higher dimensions, an idea that would leave distinct fingerprints in how the CMB's light is lensed. Even wilder theories imagine the universe as a hologram, with the CMB serving as the projection screen where deeper dimensional truths are encoded. Every anomaly in the CMB is a thread waiting to be pulled. The challenge is distinguishing true cosmic fossils from the noise of 13 billion years of cosmic evolution. Future telescopes won't just look harder, they'll look smarter, using machine learning to sift through the data for patterns no human eye could spot. What emerges might not be a single eureka, a moment but a slow dawning, a realization that the universe's oldest light has been whispering secrets we're only now learning to hear. And when we finally decipher them, the story of the cosmos may turn out to be stranger than anything we've dared to imagine. It's easy to see why the cosmic microwave background gets misunderstood. To the casual observer, the term background radiation might conjure images of static on an old TV or even the faint radioactivity lingering in our environment. But the CMB isn't just random noise. It's the oldest snapshot we have of the universe, a literal baby picture of reality. Imagine mistaking the Rosetta Stone for a random chunk of rock. That's the scale of the oversight. This isn't electromagnetic clutter. It's the afterglow of creation itself, a signal that's traveled uninterrupted for 13 billion years, carrying secrets from the dawn of time. Another common mix-up ties the CMB to dark matter or dark energy, 2 of cosmology's other great mysteries. While all 3 are fundamental to understanding the universe, they play entirely different roles. Dark matter's gravity sculpts galaxies, and dark energy drives the cosmos apart, but the CMB, it's a messenger, a fossilized echo of the universe's fiery infancy. Think of it like a crime scene. Dark matter is the invisible suspect, dark energy is the mysterious force altering the scene, and the CMB is the undisturbed fingerprint left behind, a pristine record of what happened before either of them took center stage. The confusion isn't entirely surprising. Popular science often bundles these concepts together under the umbrella of cosmic mysteries, blurring the lines between them. But here's the critical difference. The CMB is something we can see. It's not hypothetical. We've mapped it in exquisite detail, down to fluctuations 1,000,000 times fainter than its average glow. Dark matter and dark energy, by contrast, are inferred, detected only by their gravitational effects on the things we can observe. The CMB bridges that gap, offering tangible evidence of the universe's early structure, including the seeds of dark matter's cosmic web. Perhaps the most persistent myth is that the CMB is just leftover heat from the Big Bang, like the cooling embers of a fire. That's only half the story. Yes, it's thermal radiation, but the magic lies in its imperfections, those tiny temperature variations that tell us how matter clumped together in the universe's first moments. Without those fluctuations, galaxies, stars, and planets would never have formed. The CMB isn't just a relic of heat, it's a blueprint, a set of instructions written in the language of microwaves, detailing how a smooth, scorching plasma became the structured cosmos we know today. Clearing up these misconceptions isn't just academic, it's key to grasping why the CMB matters. This isn't some esoteric signal of interest only to astronomers. It's a direct line to our origins, a way to test theories about the universe's birth, growth, and ultimate fate. When we look at the CMB, we're not just staring into the past. We're holding up a mirror to reality itself, asking questions that go to the heart of existence, and the answers hidden in those ancient microwaves might just change everything. Sometimes the greatest discoveries in science aren't the result of meticulous planning, they come from pigeon droppings and stubborn static. That's exactly how the cosmic microwave background was first detected in 1965, not by astronomers peering through high-powered telescopes, but by two radio engineers wrestling with a noisy antenna in New Jersey. Arno Penzias and Robert Wilson were working at Bell Labs, trying to calibrate a massive horn-shaped antenna designed for satellite communications. No matter what they did, an annoying hiss persisted in their readings. They checked every possible source of interference near, by radio stations, military radar, even the electrical wiring of the antenna itself. Then they spotted the culprits. A pair of pigeons had taken up residence inside the antenna, leaving behind what Penzias later described as a white dielectric substance coating the equipment. Surely this was the source of the noise. They cleaned out the mess, evicted the birds, and even installed a pigeon-proof screen, but the hiss remained. That persistent hum wasn't interference at all, it was the faint whisper of the universe's birth. What Penzias and Wilson had stumbled upon was the afterglow of the Big Bang, cooled over billions of years into the microwave range. At first, they had no idea what they were hearing. It wasn't until they connected with a team of Princeton physicists led by Robert Dicke that the pieces fell into place. Dicke's group had been actively searching for this very signal, theorizing that if the Big Bang had happened, its remnant heat should still permeate the cosmos. When Penzias and Wilson described their mysterious noise, Dicke reportedly turned to his colleagues and said, "Well, boys, we've been scooped. The irony is delicious. One of the most profound confirmations of the Big Bang theory came not from a directed experiment, but from two engineers troubleshooting an antenna. Their discovery earned them the Nobel Prize and transformed cosmology from speculation into hard science. But here's what's even more remarkable: history keeps repeating itself. Just as Penzias and Wilson found the universe's oldest light by accident, modern researchers are uncovering cosmic fossils hidden within that same radiation, relics that could rewrite our understanding of physics. Take the cold spot, that mysterious billion light, ear-wide chill in the CMB. Like the original hiss in the antenna, it was first dismissed as an anomaly, a glitch in the data. But the more scientists looked, the stranger it seemed. Could it be the imprint of a collision with another universe, a tear in space-time, or just an improbable statistical fluke? We don't know yet, but the parallels are striking. Once again, what seemed like noise might be the universe's way of revealing its deepest secrets. This tradition of accidental discovery speaks to something fundamental about science. Breakthroughs rarely come from staring directly at the unknown. They emerge from the periphery, from the static we're trained to ignore. The lesson isn't just about pigeons or cold spots. It's about staying open to the possibility that the next cosmic revelation might be hiding in plain sight, disguised as interference. The CMB taught us that once, and if history's any guide, it's not done surprising us yet. The next leap in our cosmic detective story is already taking shape, not with a single telescope, but with an entire generation of them, missions like Lightbird and Pico, designed to scan the heavens with such precision they could spot a snowflake's shadow on the moon. These aren't just upgrades, they're quantum leaps in our ability to decode the universe's oldest light. Lightbird, led by Japan's space agency, will orbit from a vantage point 1,000,000 miles from Earth, shielded from our planet's heat and radio chatter. Its sensors tuned to measure the CMB's polarization down to a level 100 times finer than previous attempts. Imagine trying to read a faded, ancient manuscript under dim candlelight for decades, only to suddenly receive a high-resolution scanner that reveals every cracked ink stroke and water stain. That's the kind of clarity we're talking about, but it's not just about sharper vision. Pico, a NASA concept mission, takes a different approach. It's designed to be cold. Unbelievably cold. Its detectors will operate just a hair above absolute zero, minimizing thermal noise to catch whispers from the early universe that would otherwise drown in the static of space itself. Together, these missions form a tag team, each tackling different slices of the CMB's secrets. Lightbird will hunt for the elusive B-mode polarization patterns, the smoking gun of primordial gravitational waves, while Pico ultra-sensitive instruments could spot anomalies so subtle they've escaped every previous survey, like finding a single misspelled word in a library of billions of books. What's truly electrifying is how these missions might answer questions we haven't even thought to pose. When the Hubble Space Telescope launched, no one predicted it would revolutionize our understanding of dark energy. Similarly, the anomalies Lightbird and Pico uncover could crack open entirely new fields of physics. Maybe they'll find evidence of cosmic strings, those hypothetical space-time cracks that could rewrite gravity. Or perhaps they'll detect a statistical fingerprint of the multiverse, a pattern so bizarre it forces us to confront the idea that our universe is just one bubble in an infinite cosmic foam. The technology behind these missions reads like science fiction. Lightbird detectors use superconducting materials that lose all electrical resistance at frigid temperatures, turning them into exquisitely sensitive thermometers for the cosmos. Pico design includes a spinning half-meter lens that scans the sky in sweeping arcs, filtering out galactic dust with unprecedented precision. These aren't just tools, they're time machines built to peer past the surface of the CMB and into the quantum chaos of the universe's first trillionth of a second. Yet the greatest challenge isn't technical, it's interpretive. With data this precise, every fluctuation, every blip, could be a potential fossil or just another cosmic mirage. Distinguishing between the two will require algorithms trained on mountains of simulated universes, sifting through petabytes of data to spot patterns no human eye could discern. It's like listening for a single wrong note in a symphony performed by an orchestra of trillions, except the sheet music might be written in a language we don't yet understand. The stakes couldn't be higher. If these missions confirm inflation's wildest predictions, we'll have incontrovertible proof that the universe expanded faster than light in its infancy. If they find nothing, it could mean our foundational theories are missing something profound. And if they uncover something utterly unexpected, well, that's when the real fun begins. The CMB has been surprising us since Penzias and Wilson heard its hiss in their antenna. With Lightbird and Pico, we're not just turning up the volume, we're learning to listen for harmonies we never knew existed. Imagine waking up one morning to the news that scientists have found definitive proof of a multiverse, an actual cosmic fossil showing our universe once brushed against another. This wouldn't just be a breakthrough for physics, it would send shockwaves through every corner of human culture, from Sunday sermons to late-night philosophy debates. For millennia, we've framed our existence within a single, contained cosmos, a stage where humanity plays a central role. But what happens when that stage turns out to be one of countless identical theaters, each with its own version of reality? The implications wouldn't just challenge textbooks, they'd force us to confront existential questions we've barely begun to articulate. Religious traditions across the globe have origin stories deeply tied to a singular creation event. Whether it's the biblical "Let there be light," the Hindu cyclical universe of Brahma's breath, or the Big Bang itself as a secular creation myth. A cosmic fossil suggesting our universe is one bubble among infinite others could unsettle these narratives, not by disproving them but by expanding the canvas beyond recognition. Some might see it as validation evidence of a creator even more vast than imagined. Others could interpret it as a threat, a scientific overreach into domains once reserved for faith. History offers a sobering parallel. When Galileo pointed his telescope at Jupiter's moons, it wasn't just a discovery, it was a heresy trial waiting to happen. The difference now, the evidence would be etched into the fabric of reality itself, impossible to ignore or suppress. Philosophy wouldn't fare any easier. Thinkers from Aristotle to Kant built frameworks assuming a unified, coherent universe. But if a cosmic fossil revealed traces of pre-Big Bang physics or a multiverse, even basic concepts like causality could unravel. What does beginning mean if our universe is a branch on an infinite tree? How do we define uniqueness if every possible version of ourselves exists somewhere? These aren't abstract thought experiments, they're questions that could reshape law, ethics, and our sense of self. If free will already feels like a slippery concept, try wrestling with the idea that every choice you make spawns a new universe where the opposite happened. Society's reaction would likely swing between awe and existential dread. Some would embrace the cosmic vastness as liberating, a proof that humanity's mistakes or triumphs are just drops in an infinite ocean. Others might spiral into nihilism, asking what meaning life holds if we're inconsequential even in our own universe, let alone a multiverse. Pop culture offers glimpses of this tension. Films like Everything Everywhere All at Once turn the multiverse into a playground of possibilities, while novels like The Three-Body Problem explore the terror of cosmic insignificance. Reality, of course, would be messier, a slow reckoning with truths no single ideology is equipped to handle. Yet there's another possibility, that such a discovery could unite us. Faced with evidence that reality is stranger than any one tradition imagined, humanity might finally outgrow its tribal divisions. After all, it's harder to argue over earthly borders when you're staring at a sky full of universes. A cosmic fossil wouldn't just be a relic of physics, it could become the ultimate Rorschach test, revealing not just the universe's secrets, but our own hopes, fears, and capacity for wonder. And that, perhaps, is the most profound implication of all. A discovery like this wouldn't just rewrite astronomy textbooks, it would send shockwaves through the very foundations of how we understand reality. Picture the moment when quantum mechanics first shattered classical physics' comfortable certainties, or when Einstein's relativity revealed that time and space were fluid rather than fixed. This cosmic fossil could trigger that same seismic shift, but across multiple disciplines simultaneously. For physicists, it might finally bridge the century-old chasm between quantum theory and gravity, two frameworks that have stubbornly refused to reconcile. The tiny irregularities in that ancient light could reveal how space-time behaves at scales smaller than an atom, offering clues to a unified theory that's eluded even Einstein. Astronomers would suddenly have a new lens for interpreting the cosmos' largest structures. Those faint temperature variations in the CMB aren't just artifacts, they're the seeds of galaxy clusters and cosmic voids. A confirmed fossil could explain why the universe clumped together in precisely this way, whether through collisions with other universes, quantum entanglement on a cosmic scale, or some mechanism we haven't yet conceived. It would be like finding the missing instruction manual for the cosmos, revealing why some regions became dense with galaxies while others stretched into emptiness. But the tremors wouldn't stop at the hard sciences. Philosophers have wrestled for millennia with questions about existence, causality, and whether reality has an ultimate purpose. A concrete sign of pre-Big Bang physics or a multiverse would thrust these abstract debates into startling new territory. Imagine debating free will when there might be infinite versions of yourself making different choices in parallel universes. Or reconsidering the anthropic principle, the idea that our universe seems finely tuned for life. If we're just one bubble in an infinite cosmic foam where every possible configuration exists somewhere. Even mathematics could feel the ripple effects. The equations describing cosmic inflation or quantum gravity rely on abstract symmetries and geometries. A genuine fossil might reveal new mathematical structures, perhaps higher dimensional shapes or topological quirks that only manifest at energies beyond anything we can recreate. It's like discovering a Rosetta Stone written in a numerical language we're only beginning to decipher. The most profound impact, though, might be on how humanity sees its place in existence. For all of recorded history, we've framed our stories within a single, comprehensible universe, evidence of something beyond whether other universes, cyclical time, or a deeper layer of reality would force a reckoning as profound as Copernicus displacing Earth from the center of the cosmos. Except this time, it's not just our planet being demoted, it's our entire reality becoming one thread in a tapestry vaster than we dared to imagine. Yet perhaps the most exciting possibility isn't the answers this fossil might provide, but the new questions it would unleash. Every paradigm shift in science has opened doors to mysteries we couldn't even formulate before. If the CMB's anomalies do point to something extraordinary, they won't just solve puzzles, they'll reveal how much deeper the rabbit hole goes, and that's where the real adventure begins. What if you didn't need a billion-dollar telescope or a PhD in astrophysics to uncover the universe's deepest secrets? The hunt for cosmic fossils isn't just for professional scientists, it's a treasure hunt open to anyone with curiosity and an internet connection. Projects like CosmoQuest and Zooniverse have turned the analysis of cosmic microwave background data into a global collaboration, where teachers, students, and even amateur astronomers can sift through real telescope data from their living rooms. Imagine scrolling through patches of the CMB on your laptop, flagging unusual temperature fluctuations that might, just might, be the imprint of a cosmic string or evidence of a multiverse. This is citizen science at its most thrilling, the democratization of discovery, where a retiree in Tokyo or a high schooler in Buenos Aires could stumble upon a clue that rewrites cosmology. The beauty of these initiatives isn't just in their inclusivity, it's in how they reframe our relationship with the cosmos. For centuries, astronomy was the domain of elites with access to observatories and institutions. Now, the universe's oldest light is a shared canvas, inviting everyone to contribute brushstrokes to humanity's collective masterpiece. When volunteers comb through CMB data, they're not just clicking buttons, they're participating in a lineage of exploration that stretches back to Galileo. And sometimes they spot what algorithms miss. Human intuition has a knack for recognizing patterns machines overlook, whether it's an odd alignment of hotspots or a cold patch with peculiar edges. In 2010, a Dutch schoolteacher poring over data from the Planck satellite helped identify a rare type of gravitational lensing in the CMB, proving that fresh eyes can see what supercomputers sometimes skip. But the impact goes beyond scientific output. These projects foster something rarer, a visceral connection to the cosmos. There's a difference between reading about the Big Bang and actually tracing your finger across its afterglow on a screen, knowing your observations might end up in a published paper. It transforms abstract science into something tactile, even intimate. One volunteer described the experience as time traveling to the universe's infancy, a sentiment no textbook could replicate. And when discoveries emerge, like the tentative identification of anomalous ring structures in the CMB by citizen scientists in 2018, the celebration is communal. The thrill isn't confined to ivory towers. It ripples through forums, classrooms, and dinner tables, sparking conversations about quantum physics in places it might never have reached otherwise. What's often overlooked is how these projects safeguard science's future. By inviting the public to engage with raw data, they demystify the scientific process, showing that research isn't a series of eureka moments but a grind of careful scrutiny and collaborative problem-solving. A teenager tagging CMB anomalies today might be the astrophysicist leading a NASA mission tomorrow. And in an era where misinformation spreads like wildfire, hands-on involvement builds trust in science itself. When you've passed the same datasets as professionals, you're less likely to dismiss their conclusions as elitist or opaque. Yet the most profound outcome might be philosophical. In a universe that often makes us feel small, citizen science offers agency, a reminder that cosmic truths aren't locked away but scattered like stardust, waiting for anyone bold enough to reach for them. Whether it's classifying galaxies or hunting for primordial black holes in the CMB, these projects whisper an exhilarating truth. The universe isn't just something we observe. It's something we explore together, and sometimes the next great discovery isn't hidden in the depths of space, but in the curiosity of someone halfway across the world, clicking through the static of time itself. The cosmic microwave background isn't just a window into the universe's past, it's a masterclass in how science works, a living textbook that teaches us as much about curiosity and perseverance as it does about cosmology. Every fluctuation in that ancient light is a lesson waiting to be unpacked, showing students and researchers alike how to ask questions, challenge assumptions, and follow evidence wherever it leads. Take the story of Penzias and Wilson, those engineers who mistook the Big Bang's echo for pigeon interference. Their journey from frustration to Nobel Prize is science in its purest form, stumbling onto something profound precisely because they refused to ignore the unexplained. That's the power of the CMB. It turns abstract concepts like the scientific method into something tangible, something you can almost reach out and touch. For educators, the CMB is a goldmine. Imagine teaching physics with a dataset that spans the entire sky, where students can analyze the same primordial light that professionals study. Projects like the Sloan Digital Sky Survey have already made chunks of this data accessible, letting classrooms measure temperature variations, map density fluctuations, and even hunt for anomalies, just like real cosmologists. It's one thing to learn about redshift in a lecture. It's another to calculate it yourself using photons that have traveled since the dawn of time. The CMB doesn't just illustrate the universe's evolution, it lets students retrace its steps, discovering for themselves how a sea of plasma became galaxies, stars, and planets. But the real magic lies in how these cosmic fossils inspire wonder. There's a pivotal moment when a student realizes those blotches on a CMB map aren't just abstract data points, they're the blueprints for everything we see today. That revelation sparks something primal, the same awe that drove ancient cultures to map the stars. Only now the questions are even bigger. What if the cold spot is a bruise from another universe? Could those faint swirls in the polarization reveal quantum gravity? The CMB invites anyone who engages with it to think like a detective, piecing together clues from the ultimate cold case. Universities and research centers are leaning into this potential. Programs like the Perimeter Institute's Einstein Plus workshop train teachers to bring cosmology into K-12 classrooms, using the CMB to bridge physics, math, and even philosophy. Meanwhile, citizen science platforms like UNIVERSE let high schoolers contribute to cutting-edge research, classifying anomalies that could lead to breakthroughs. It's a far cry from memorizing equations. This is science as exploration, where every participant, regardless of age or expertise, gets to share in the thrill of discovery. Perhaps the greatest lesson the CMB teaches is humility. Staring into that microwave static, we're confronted with how much we don't know. The anomalies that don't fit our models, the whispers of physics beyond our grasp. They're reminders that science isn't a static set of facts but an ongoing conversation. And that's a message that resonates far beyond astronomy. Whether you're a student grappling with your first research project or a seasoned physicist questioning decades-old theories, the CMB whispers the same truth. The universe is vast, mysterious, and always ready to surprise us. So the next time you see that grainy CMB map, the so-called baby picture of the universe, remember it's more than a relic. It's an invitation to question, to explore, and to dream bigger. Because somewhere in that cosmic static, there might be a discovery waiting for you to uncover it, and that's the most powerful lesson of all. Somewhere in the faint static of the cosmic microwave background, there might be clues pointing to realities far stranger than we've ever imagined. Realities where the universe isn't a one-time event but an endless cycle of rebirth, where our three-dimensional world is a holographic projection, or where time itself didn't begin with the Big Bang. These aren't just wild sci-fi concepts. They're serious, if speculative, frameworks that physicists use to make sense of the anomalies in that ancient light. Take the idea of a cyclic universe, for example. Picture a cosmic accordion, expanding and contracting over eons, each Big Bang, not a beginning but a turning point in an infinite loop. The CMB's temperature patterns could hold subtle evidence of this, stretches and compressions in space-time left over from a previous cycle, like wrinkles in a sheet of paper that's been folded and unfolded too many times. Certain irregularities in the microwave background, like unexpected large-scale correlations between seemingly unrelated regions of the sky, might be the echoes of a universe that came before ours, its gravitational waves imprinted onto our own infancy. Then there's the holographic principle, a theory so mind-bending it redefines reality itself. Imagine the universe as a two-dimensional surface, like the security sticker on a credit card, with all the richness of our three-dimensional world somehow encoded on its flat plane. If this sounds impossible, consider how a hologram works. Shine light on a flat, patterned surface, and a three-dimensional image appears. Some physicists suggest the CMB could be that surface, its fluctuations not just random noise but pixels in a cosmic projection. If true, those tiny temperature variations might actually be bits of information, a code written in the language of thermodynamics and quantum gravity. The cold spot, a glitch in the matrix, the axis of evil, a smudge on the lens of reality. But perhaps the most radical idea is that the Big Bang wasn't the absolute beginning. That time, in some form, existed before it. Certain models, like loop quantum cosmology, propose that our universe emerged from the collapse of a previous one, a big bounce rather than a bang. Others suggest space-time itself is eternal, with our observable cosmos just one bubble in an endless froth of universes, each with its own laws of physics. If traces of these pre-bang conditions survived inflation, they'd be hiding in the CMB's most primordial fluctuations, like fossils buried deep beneath layers of cosmic sediment. The challenge is distinguishing these relics from the noise of 13 billion years of cosmic evolution, a task akin to finding a single, specific grain of sand on all the beaches of Earth. What makes these theories so compelling isn't just their audacity, it's that they're testable. The cyclic universe predicts specific patterns in the CMB's gravitational wave background. The holographic principle implies mathematical relationships between entropy and surface area that could be checked against observations. Bouncing cosmologies leave distinct signatures in how matter clumps at the largest scales. Even if they're wrong, they push science forward by forcing us to ask better questions. After all, the greatest breakthroughs often come not from confirming what we already suspect, but from discovering that reality is far weirder than we dared to dream. So while these ideas may sound like the stuff of late-night philosophy debates, they're grounded in real data, real math, and real curiosity about the anomalies that refuse to fit neatly into our textbooks. Whether they're ultimately proven true or not, they remind us that the universe's oldest light isn't just a relic, it's a mirror reflecting back not just our past, but the limitless possibilities of what might lie beyond. The cosmic fossil embedded in the microwave background isn't just a relic, it's a cipher waiting to be cracked, a message from the universe's first breath that could redefine everything we know about existence. Think of it as the ultimate cold case, one where the clues have been scattered across 13 billion years of cosmic evolution, and the stakes are nothing less than understanding the very fabric of reality. What makes this search so electrifying isn't just the potential answers we might find, but the sheer audacity of the questions we're forced to ask. Could those faint temperature fluctuations be the fingerprints of a multiverse? Does the cold spot hint at a collision with another reality, or is it evidence of dimensions we can't yet perceive? This isn't just theoretical musing, it's science at its most daring. Every anomaly in the CMB is a crossroads where established physics meets the unknown, where the comfortable certainties of textbooks give way to thrilling possibilities. Take inflation theory, for instance. The idea that the universe expanded faster than light in its first moments was once met with skepticism. Now it's a cornerstone of cosmology. But what if the CMB's irregularities reveal that inflation wasn't uniform, that some regions of space-time stretched more than others, leaving behind cosmic scars? It's like discovering that the map of the world you've been using is missing entire continents. The beauty of this pursuit lies in its universality. You don't need a particle accelerator or a space telescope to appreciate what's at stake. That static on an old TV, it's the same static that holds the universe's origin story, the warmth of sunlight, a distant cousin to the primordial glow we're decoding. This connection between the mundane and the cosmic is what makes the CMB so extraordinary. It bridges the gap between human-scale experience and the grandest scales of existence. As we stand on the brink of potentially earth-shattering discoveries, it's worth remembering how far we've come. A century ago, astronomers debated whether the Milky Way was the entirety of creation. Today, we're probing the universe's first trillionth of a second, using light that's older than stars themselves. The tools may have changed, from glass plate photographs to superconducting detectors chilled near absolute zero, but the essential human impulse remains the same: to look up and wonder. What comes next could rewrite the story of everything. Maybe the next breakthrough will come from a graduate student spotting an odd pattern in the data, or a citizen scientist poring over telescope images from their living room. Or perhaps the crucial clue is already hiding in plain sight, waiting for someone to see it differently. One thing's certain, the universe isn't done surprising us. Every time we think we've glimpsed the edge of understanding, it recedes like a horizon, revealing new mysteries to chase. So keep watching that static. Listen to its whispers, because somewhere in that cosmic noise might be the answer to questions we haven't even learned to ask yet. And when we find it, we won't just be uncovering the past, we'll be charting the future.